The fast Fourier transform. One of you asked me to talk a little bit about this. So we have seen that we can take f of x, and if we're considering a periodic function over minus pi to pi, we can think of its Fourier series as representation of the function. And that is in the ideal situation in which we know the function completely, then we can have a Fourier series with as many terms as needed to combine all the information we have about the function itself. This is not usually the setting when we're looking at numerical analysis. We have finite information, so we cannot have infinite series just because the information that we have is not infinite. So we are thinking of, instead of knowing f of x all the time for every value of x, we actually only know f of xi for a finite number of xi uniformly distributed between minus pi to pi. By uniformly distributed, I don't mean it in the statistical sense, I mean that they are spaced equally from minus pi to pi. So if you have an information about f of xi for a finite number of points xi, then you can compute a truncated Fourier series. And if you're doing the checks numerically, it doesn't make sense to compute more than the complex Fourier coefficients with indices ranging from minus n divided by 2 to n divided by 2. The idea is that the information that you have about the function doesn't increase while you're doing the Fourier transformation. So you have to have the same information in the phase space as you have in the sequence space. Applying a Fourier transform is not a magical way to get more information, it's just a way to get different information. So now that we have this correspondence, we want to actually be able to compute it. Analytically, we know that computing Cn, so a Fourier coefficient, is an integral from minus pi to pi of f of x times e at the minus I knx, with kn being equal to n on the interval minus pi to pi. So this is a complex exponential. We can replace it with a Riemann sum, with the idea that is, we are computing the values of f at the xi's in which we know it. So this is the best Riemann sum we can build out of the information that we have. We don't have more information than that. What is the problem by applying this Riemann sum straightforwardly? It is very slow. For every single value of your Fourier series that you want to retrieve, you have a sum spanning every value that you have of your function. So you see how this just stores a lot of information. It's going to take a lot of time to just compute. So the Fourier FFT stands for fast Fourier transform, and it's just a numerical algorithm to compute Cn based on f of xi that is much faster than any other known algorithm. So the idea behind the algorithm is that the exponential of minus I knxi with n spinning around, with n increasing, is not a random value. It's a value that has a lot of structure. It's actually a value on the complex circle. So if you can track where it goes and keep track of where it is, it's faster than just going blindly and brute forcingly compute it. So to be more precise, your initial algorithm that was just brute forcing the Riemann sum took a time that was a coefficient times n squared, when n is the number of Fourier sequences that you Fourier coefficients that you want to compute. So if you add n number of new coefficients that you want to compute, this goes up at the speed of n squared. While the new fast Fourier transform algorithm takes time proportional to n log n, where the logarithm can be taken in any base that you can. So you can take a very large base logarithm that grows slower. Why is it so important? Because this is the difference between being able to do some calculations and not being able to do some calculations. So the development of the fast Fourier transform actually meant that using Fourier transformations and coefficients was actually possible. Now we have much stronger computers that could handle also the brute force approach, but really this was a major change in numerical analysis. And as we have the fast Fourier transform in one direction, we have the inverse fast Fourier transform for the inverse Fourier transform, obviously.